why the hell am I talking about lightsabers? What qualifies me to talk about lightsabers? Can anyone either wave your hands crazily or write in the chat box if they've got any ideas as to why you think I should be talking about lightsabers?
Because you worked with plasma and lightsabers use plasma.
That's exactly right. So here's a little screenshot that I've taken from Wikipedia, which is one of the nerdiest places on the internet. So that's where you can find everything you wanted to and even didn't want to know about Star Wars. And you can see on their entry on lightsabers, it says lightsabers consist of a plasma blade. So they're a blade of plasma. So that's why I'm talking about lightsabers. So I guess the first question is, what is plasma? Anyone got any examples of plasmas that they might know of? Yeah, plasma is the state of matter.
Sun.
The sun is definitely plasma. Any others?
Lightning.
Yeah, we wrote lightning.
I thought it was
Lightning, that's a great one. Yeah, that's definitely a plasma. Okay, let me show you a slide.
Someone said stars.
Stars are definitely plasmas as well, just like the sun is. So here's just a few examples of plasmas that I've put, but there's loads more. So we can see we've got lightning, we've got the sun, and of course stars are very much like the sun. The sun is just a star. You may have seen a plasma ball. That's the one on the left of the sun there. You've also got, plasma cutters. If you're, doing industrial processes, we use plasma to cut sheets of metal and things like that. You can see on the bottom right, fluorescent lights like neon lighting and stuff like that. Those are plasmas too. And then if you've got a slightly old television, then you may have a plasma TV. They're examples of plasmas. But in fact, there are loads of others, because plasma is almost everywhere. As we've said, some people said, it's a state of matter. It's the most common state of visible matter, about the matter that we actually understand. There's something like 99% of the universe is in the plasma state. It's not solid, liquid, or gas. And to give you a bit more on what plasma actually is. So, we can take atoms like this, and if we ionize atoms and we have these ions and free electrons going around, and that's what a plasma is. It's a gas of charged particles, an ionized gas, but it's slightly more than just an ionized gas. There's something that makes it a bit more special than that, because you may know, a charged particle feels electrostatic forces. It feels, and it basically has an electric field around it. So if this is a positively charged particle here, any minute we'll see a load of arrows pop up, which will show you what would happen if you had another charged particle placed at that location. That's what we call an electric field. And so each of these charged particles that we've got in the plasma will add to the electric field, but then they'll also be influenced by the overall electric field. And what that can do is you can get some very weird collective effects going on. And similarly, not just electric fields, magnetic fields as well. So, if you have a moving charged particle, then that creates a magnetic field. And so you can get similar things going on like that. So that's really what makes plasmas a bit more special than just a gas, or even just saying an ionized gas. They have this sort of weird collective behavior that makes them far more complicated and interesting. And that's why scientists are still studying them. Okay, so now we know that lightsabers are a plasma blade. I've got another question for you. Does anyone have any ideas as to how lightsabers glow? Actually, okay, so we've got someone that says like a neon light. Yeah, we'll talk about that in a sec. Any other ideas as to, and also someone said because very high energy from there. So actually, I think we've covered both bases. Let me go into a little bit more detail about this. Okay, there are two ways I can see that you can make a lightsaber glow. Both of them actually stem from quantum physics. Both of them. Quantum physics, of course, being that sort of weird world of the atomic and subatomic, where particles can act a bit like waves, and it completely revolutionized our understanding of the universe. Now, the first way is the way that somebody mentioned, like neon lights. We can use the fact that in quantum mechanics, electrons around the nucleus of an atom form quantum states. They form in these specific energy levels. They're not allowed to be in any place. They have to form in very well-defined states, which have very well-defined energies. And you can see these here for the hydrogen atom. So you have the ground state, which is the 1s. Then you have the 2 level, the 3 level, and they've got substates in there. And all of these arrows, all these red arrows, indicate all of the transitions that you can go, an electron can go from being in an excited state back down to a lower energy state by emitting a photon of light. So it can't do it for all of them. There are only certain ones that it can transition, and they're given by those red things there. So what essentially that tells us is those are the packets of light that are able to be emitted by a hydrogen atom. And so essentially that kind of tells you that hydrogen will have a specific set of colors that it can emit. Anything else isn't allowed. So we can look at some other examples of colors being emitted from various. So this is what hydrogen looks like. Helium has a slightly different color, mercury a different color, neon completely different color. So that's a fingerprint of the substance that you're actually using. So that could be one way. That's how neon lights work, is by whatever you put in, whatever you ionize as the plasma, you excite it, it relaxes down, and that's how you color it. The other way is the way that the sun and stars work, is by being incredibly hot. Now you might think, well, why does that have anything to do with quantum mechanics? Well, this was one of the very first bits of quantum theory that was actually worked out. It was done by Planck himself. So if you look at the spectrum of light emitted from a hot body, otherwise known as a black body, it's given by this here, and we can see, you know, the visible light. And if you look at the top right, you can see what the overall color is as we go up in temperature. So we're going through to white, it's getting white hot, and it should now go into blue like so. And it was red earlier. We'll play it again. But you can see it has this shape. So it's emitting at lots and lots of different frequencies of light, you know, through the UV into the infrared and stuff like that. But we weren't able to work this out theoretically using our old theories, our classical theories that didn't have quantum mechanics, that essentially didn't have photons, didn't have quantized packets of light. It seemed to think that even like your oven in your kitchen should be emitting infinite amount of energy, which is a load of rubbish. So it wasn't until quantum theory came along that we actually could solve this. So that's another way. So we could have it being incredibly hot, like glowing red hot or glowing blue hot for lightsabers. And just to tell you what that would be. So we're talking, if you were on the dark side, you'd have a blade of 1,000 Kelvin to get a red lightsaber. But if you were a Jedi, then for blue, you're talking 15,000 Kelvin. That's pretty damn hot, okay? And actually that probably helps you, because what the lightsabers good at doing, they're good at cutting through almost anything. So they can melt through materials. So I think this is probably the way to go for something that acts a bit like a lightsaber in real life. It does mean, though, you couldn't get a green lightsaber, and you certainly couldn't get Mace Windu's purple lightsaber. You can't have a green one. If you do that, then you're going to have a slightly less hot one made out of some substance that emits green, probably some form of oxygen. I can't remember which one it is.
So I could like chop through a door with it? Probably not. Oh.
You probably couldn't chop through a door with a green lightsaber. So I'm going to go with it being incredibly hot. Though everything else I tell you about today, you know, it still could work for the less hot versions. The numbers might change only a tiny bit, but not by very much. Okay, so we've solved how to make lightsabers glow with light, but how do you make a lightsaber into a plasma blade? How do you contain it? Because otherwise, you know, just like gas, it's going to want to expand and just spread out all over the place. So again, I'm going to ask a question. Does anyone have any ideas before I tell you about my solution?
It's a device like what? Hot metal, a mirror, high frequency, a mirror. Anyone else?
Mirror, okay. Mirror would work if it was actually like a laser, but we're doing a plasma blade, so maybe not.
Yeah, we know it's a plasma plate, but anything else?
Oh, magnetic field, great job.
Okay, somebody's written in the chat, magnetic field. And that is right on the money. It might be able to do something with high frequency radio waves, but I think that'd be a bit very, very complicated. So somebody did say something about high frequency. Possibly, but I think a more conventional route would be to use a magnetic field. Has anyone seen something like this before? This is called a tokamak. It's a sort of nuclear fusion reactor. And essentially what it does is it's counteracting the high pressure of the plasma by virtue of it being incredibly hot, by using the fact that magnetic fields also exhibit pressure. So you can actually confine the plasma by using a very strong magnetic field. And that's why you can see that here the plasma is nice and contained within a tube and not hitting the walls and making everything ionize and destroying the whole experiment.
Wait, so there's no glass or anything restricting this?
There's absolutely no glass. It's all magnetic fields. That's just a magnetic field keeping it in a sort of cylindrical shape that has then been turned into, it's like a big donut essentially of plasma that's been kept in place purely by having very, very strong superconducting magnetic fields. That one's at UCLA, by the way,
when you say
LA.
superconducting, what do you mean?
Superconducting, that's just the way that we get around making very big magnetic fields. So, you know, if you've got current going through a wire, that creates a magnetic field. You can coil that up and you'll get bigger magnetic fields. But you sort of hit a bit, you hit a bit because, you know, more current going through a wire, it heats up. That's not great. Superconductors have this amazing property that if you cool them down below a certain temperature, there's absolutely no electrical resistance.
Okay.
So you're not losing any energy to heat in the way that you would do normally. And that's the way you can get out very high magnetic fields. That's what they do.
Because nothing's stopping the current, so it just keeps flowing.
Exactly.
Just keeps generating magnetic fields.
Pretty much, yeah. So, for instance, at the Large Hadron Collider, they use this to keep their particles going around the ring, and they use 8 Tesla magnetic field in the actual big ring bit.
So they could be making one of these red lightsabers.
Well, exactly. So you can see here. So, you know, for a red lightsaber, you're talking 6 Tesla magnetic field. So that's doable. We've got things that do. Okay, obviously, you're going to try and create 6 Tesla using just like a handheld size hilt, whereas the actual magnetic fields, the superconductors in the LHC are a bit bigger than that. But in theory, you can do it. And in fact, for a blue lightsaber, because we know that has to be a lot hotter, we're talking 23 Tesla. That's still doable. That's nowhere near. Well, it's not over the strongest magnetic fields that we've been able to produce continuously. So from that point of view, we should be able to construct a plasma blade that can be confined by a magnetic field. That's fine. Another little bit of cool plasma physics actually helps us out as well. So when you've got a magnetic field and a plasma, there's this thing called the frozen-in approximation or the frozen-in condition. And what that essentially means is that magnetic fields are almost like they're frozen into the plasma. They're stuck with it. So that if a plasma moves, then the magnetic field moves with it. Or if you want to think about the magnetic field moves, then the plasma moves with it. They're tied to one another. And that has this nice sort of repercussion that if you've got 2 different plasmas, 2 completely different plasmas, say lightsaber 1 and lightsaber 2, you try and bring them together and they won't want to mix because the magnetic fields will be tied to one another. So those plasma blades should clash. So it seems like this is the great thing you want, because you don't want to be losing the plasma all the time if you just swing it around and having to constantly refuel it. That would be terrible. And you also don't want a lightsaber that just swings through the other lightsaber like you would have if it were a true laser sword. This is why we don't think they're laser swords. So it seems like we're okay. In fact, this is also, if we go back to my research a little bit, the reason why we can separate out, our magnetosphere from the solar wind. There are two different sources of plasma. The solar wind, plasma coming from the sun, magnetosphere filled with plasma largely coming from the top of the atmosphere being ionized by the sun's radiation. And you get this nice, well-defined boundary at the edge of the magnetosphere where they don't mix. And that's kind of why we have this magnetic shield. So it seems like, from a physics point of view, lightsabers should be possible. Now, I brought up Boromir because, yes, one does not simply just build a lightsaber. There's a lot of technology problems, okay? So whilst, from a very basic physics point of view, it should be feasible, we do have to worry about how much energy is it going to take. Huge amounts of energy to create those
sure. Like you need
those
the
15,000 Kelvin plasmas, and then the 20 odds, the 15 odds Tesla magnetic field. So there's a lot of that. And then how do you condense that down into a hilt? But these are technology problems. They're sort of engineering problems. So they're not physics problems. And so therefore I could say, well, lightsabers should be possible. There's nothing against them being possible. If the blade is so hot, you could burn. Yes, you could totally burn your hand. You should wear gloves. So definitely wear gloves. Very, very, very thick gloves. But they will be emitting some radiation.
Or could you have little magnetic gloves that also contain the plasma?
Again, this is an engineering thing. So yes, feasibly, yes. You just have to worry about an engineer to sort of design this sort of thing.
So if they want to build their own lightsabers, they need to make magnetic gloves and the lightsaber itself.
Maybe, yes, for safety reasons, health and safety, and all that. Except there is one problem. So I told you that there was this frozen-in condition, and that's why lightsabers can clash. But that frozen-in condition does sometimes break down in a process called magnetic reconnection. And there's a GIF of this showing here. So if you can imagine, you're bringing two lightsabers together. So we've got the red lightsaber coming down from the top, the blue lightsaber coming up from the bottom. And you can see here, they're not clashing. They're, in fact, the magnetic fields are changing, and you're getting these outflows on the left and the right. And what that's doing is it's not only releasing that plasma that was in the lightsabers, it's also releasing a lot of the energy that was tied up into the magnetic field. So magnetic reconnection is a really important and fundamental process in plasma physics. We're still trying to understand at some very, very small levels. It's incredibly important. One reason being, like for Earth's magnetosphere, you can see here, if you get an eruption of plasma coming from the sun, and if its magnetic field is oriented in just the right way, when it ends up hitting Earth's magnetic fields, it can cause Earth's magnetic field to break down. And so we see it opens up, releasing lots of energy into our magnetic shields. And then that process will then occur again on the far side of the Earth in the tail, which will happen now. And then that's putting loads of energy into electrons, which stream along those field lines, hit the top of the atmosphere, and cause things like the aurora, and can cause real problems for our technology.
So if you had a lightsaber fight,
yeah,
and your lightsabers clash and hit each other, you could potentially generate aurora on your face.
Yes. So, okay. I mean, it's even worse than that, because if you work out the speed that the plasma would be ejected from your lightsaber clash, it's around 3,000 to 13,000 meters per second. That's the speed of most explosions. So you're literally causing an explosion of super hot plasma, as hot as parts of the sun, which is then going to hit various parts of your body. And the worst thing is, when we saw it with the sun and the Earth, that usually only happens when the magnetic fields are almost oppositely aligned, okay? And other times it doesn't always happen. But with the conditions you have in a lightsaber, almost every single time two lightsaber blades, every conceivable clash of lightsabers would cause reconnection to occur. So you would get an explosion happening every single time you hit two lightsabers together, which is not good news for either of you. So that's why I call this the fundamental flaw with lightsabers, because it's a fundamental piece of plasma physics that you just cannot get around with any clever engineering. And that's why I have now decided that I don't want a lightsaber anymore.
But if you didn't get in a lightsaber fight, you'd be totally
So
fine.
it would be totally fine if you were the only person with a lightsaber in the universe.
So Trafford School, and Miss Lee, someone at Trafford School said, would the magnetic fields not attract or repel one another?
Yeah, so depending on how you design them, then yeah, you could get a little bit of repulsion going on between the magnetic fields to stop them going. But the thing is, if you get them close enough, then this goes on. And if you're really putting some force into it, then it's pretty much clear that the lights. So you'll get some repulsion just because you're squashing two magnetic fields together that don't want to go. Just like if you try and squash two magnets together that don't want to go. But you know, if you squash hard enough, and you know, particularly in some of the later films, they're really going for it with the fights. So
you could get past the repulsion.
You get past the repulsion as long as it gets close enough that the two plasmas can start interacting. And if you've got very hot plasma, then it's not that distance doesn't have to be that much, right? Because these things are gyrating around so actually I think reconnection really is a big problem, and the magnetic fields aren't enough.
And then you just get explosion after explosion.
Yeah, if you're not killed by the first one.
How many megatons would the explosion be?
How many megatons?
Oh my God, how many megatons? That's not an SI unit. Don't use megatons as a unit. It's a terrible unit. I think it's probably comparable to some sort of nuclear explosion, surely, because you're hotter than most nuclear bombs, right? Because they're mostly, or at least the early ones were fission bombs. So, and you're about as hot as the top of the sun. So I think that it's a lot. I don't have a specific number for you because I'd have to get a calculator out, but it's a lot, and it's going incredibly fast. I think the real thing is you're going to be hit by a shockwave of, 3,000 meters per second at least plasma. I think we've got another question.
So James has an understanding, who's hiding at the back behind the folder there.
Sure.
Right.
The tokamak, you're saying that the magnets are on the outside and the plasma stream runs through the middle, so wouldn't you need the magnets on the outside of your lightsaber?
Oh, a very smart question.
Yeah, so you'd have to do some very clever design work on how to. You do need that really strong magnetic field on the outside. Like in the tokamak, you've got those big coils of plasma on the outside, like so. But I mean, Michio Kaku came up with an idea. It's not quite like the lightsabers that you see in the films, but if you had a sort of ceramic sort of thing, which was then leaking the plasma, and then that had coils of wire around that, then that would sort of do it. And you'd just get you'd get a little bit of the plasma sort of leaking out the sides. So that's a sort of an engineering question as how you actually design that. But I think you can get around it. It should be possible.
So we had another question from Liverpool.
So like in the films when they are sort of fighting each other and they sever limbs and different things like that, would it cauterize the wound, or would it just sort of outright kill them for temperature wise and things like that?
I mean, it would totally melt the part of you that went through. So yeah, I don't think it would cauterize the wound, because you pretty much just melted part of them. So that's not quite the same as just like a burn, like fire hot that would do that. So I'd say it would definitely not be good for you. I wouldn't advise doing that.
I mean, it sounds pretty bad. If you start your lightsaber fights, it's not going to end well.
No,
you're just
any of
exploding
them
every time.
Yeah.
Don't do it, I think, is the lesson from this.
Wait a second. Go on, ask. Try.
Can it run out of power?
No.
Did you have another question?
There was a, would it run out of power? With conventional power generation, yes. It's going to take a huge amount of power to make your lightsaber even work. More, I mean, you can't use batteries. It wouldn't be cordless at the moment with our current technologies. But again, this is the thing I'm saying, that's an engineering problem. You know, that's a technology problem.
So the science doesn't stop you.
The science doesn't stop you. It says it's feasible, doesn't say we can actually do it now. So yeah, at the moment, I don't think we can really generate that amount of power, and certainly not in a compact way that would make it useful. But yeah, the power thing is one of the things that would hold us back from even trying to make one right now.
Oh, I really like this question from Trafford. So how powerful is the Earth's magnetic field in comparison?
Oh, it's pathetic. Utterly pathetic. It's the Earth's magnetic field is a 10,000th of a Tesla.
Okay, and we needed 10.
And we needed about 10 Tesla at least. So it's absolutely nothing.
So you need a much stronger magnetic field than the Earth provides.
Yeah.
Do you know any astrophysical objects that would do it?
I mean, there's quite a few. Like, I mean, the magnetic fields around some stars is of order of that sort of thing. There are some objects that have ridiculous magnetic fields. They're called magnetars, and they're a type of neutron star that's condensed its magnetic field really down, and that's like mega to giga Tesla, so like 10 to the 8, 10 to the 9 plus Tesla. So those are the strongest magnetic fields in the universe.
Wow.
But we don't need one of those for this, thankfully.
So Trafford also asked this question of, if you turn the lightsaber off, would the plasma just go everywhere?
Yes, the plasma would just go everywhere. It would just sort of disperse, so it should just spread out fairly evenly. I don't think that's too much of a problem. You might want to get out of the way a bit, but I think because it can go in all directions in that case, it should just disperse. Yeah, so I think that's not too much of a problem. Right, I think we've got do we have a question from over there?
How would you store your lightsaber?
Okay, so I mean, if you're going by my route of making a lightsaber, you just need anything that's really hot. So in fact, the thing that you could ionize is the air. You don't actually need any special materials. So
you just turn it on, and
you would just turn it on. It would heat up the air around. You turn on the magnetic field. I mean, it would probably be a bit slower to kind of come out of the lightsaber than it does in the films. You imagine it just growing very slowly, like so. That's how you do it. And when you turn it off, all of that air, that hot air, would just dissipate, and then you just have your hilt again. Your incredibly massive hilt with current technology. But
the one that's plugged into a power source.
That's plugged into the national grid. So yeah, you wouldn't have to worry too much about that. If you were using the sort of neon lights technology, then you would need your hilt would have to contain a source of whatever the material it was you were using. So whatever you were going to ionize, that would be contained within it. Oh, we've got a question.
Would a lightsaber work underwater?
Would a lightsaber work underwater? Yes, due to something called the Leidenfrost effect.
Go on.
So if you were to heat, it'd be so hot it would just vaporize. It would just make a gas. So you'd end up having just a pocket of gas around the lightsaber, which you then just swing around. So it was fine. It's the same thing that happens if you've got a frying pan and you heat it up really hot, and then you drop some water on it, and then the water's just floating on the top because there's so much. It's just vaporizing some of it. So there's a gas cushion that it just lives on, and then the rest of it is just water. So you basically get the same thing going on. Your lightsaber would be able to swing underwater with a nice air around it before it hit the water. So you wouldn't just be vaporizing the ocean the whole time, which is energy efficient.
Liverpool, did you guys have any more questions?
You got any more questions? You make a real lightsaber.
That's what the whole thing is about, Phil.
Would it ever be like realistically feasible to build one?
Probably not. So, I mean, we've kind of gotten to the point that that yes, physics allows for lightsabers to be made, but like we said, huge amounts of power required. Is it worth it? Probably not. You know, lots of technology to go through, and even if you do it, then you still got this problem that when you clash, they're going to explode. So, from my point of view, you know, if you were an inventor, you'd probably say that's not a good thing to invent. It requires more energy than we can actually make, and its whole point, which is to do like fighting, is going to be fatal. So I don't think lightsabers would ever be feasible, you know, from a realistic point of view. It's a bit sad, sorry.
A disappointing way to.
There is though.
3 minutes.
I mean, I will say you can adapt some of this technology that I've introduced for another object in the Star Wars lore, which is maybe less unfeasible. It's still got a few problems, but I have a think what that is in your head. And if you want to really find out what I'm talking about, I've got another video on my YouTube channel. You can watch that. But see if you can guess what that is before. I think we've got a few final questions, don't we?
Yeah, so we're going to have to wrap up in a couple minutes. So if you have questions on the live stream, pop them in right now. So we've got 2, so you can pick whichever your favorite is. It is, or three now. So would the Force be possible? Could nuclear fusion occur in a lightsaber? Or would lightsabers be able to deflect plasma blasters? I like the last one. Yeah,
okay, so I actually had to answer this question. A sort of friend of mine was writing a book of science of Star Wars, and he said, would it be able to deflect plasma blasters? So, you know, all of the guns in Star Wars, they send bolts of plasma as well, right? And that's possible in the same way. There's this thing called bootstrap currents. So you can set a current to create a magnetic field within the plasma to confine it for a short amount of time, so it won't dissipate. So if you were to send that out, then essentially it's almost like a detached lightsaber for a bit. So you end up running into exactly the same problem, that it hits your lightsaber, it's like 2 lightsabers clashing, you get an explosion. So that's actually quite a clever way. If you can send bolts of plasma at the one person in the universe, then you're going to blow them up, and you're going to be far away. So in that case, you're fine.
Then you've destroyed the only lightsaber in the whole universe.
Exactly.
So Liverpool have asked, how close could 2 lightsabers get without exploding?
Right. Okay. This really depends on the numbers you put in. So it depends on how hot you make the plasma, because then you can work out exactly like the gyro radius, so how far apart the particles are sort of gyrating around the magnetic field. I don't have the number off the top of my head. It's not going to be too much, and you've got to look at other scales as well. So that's really dependent on exactly what color your lightsaber is, and exactly how strong the magnetic field you actually use is. So that can be quite dependent, but it should order of magnitude not be that much. So
okay, so we probably have time for one more question. So if Liverpool Unconscious, we've not asked you guys too many questions. Do you have any more?
Oh, so didn't they ask about the Force? Did Liverpool ask about the Force?
No, that was Trafford. And
Trafford
has said, why can't you just arc the plasma? And I think
well,
this will be our last question.
Arcing is usually a bad thing, because that's the whole idea of that. It just kind of, you end up creating a current going through in an unpredictable direction, right? So it's like with lightning. Okay, that's just an arc of plasma being created between 2 points to allow that huge potential to be sort of rectified, because you don't want that. That's a lot of energy building up, and then you can just release it. So an arc is the absolute worst thing. That's pretty much worse than reconnection, or about as bad as reconnection could be. So arcing's not great. It would just jump and uncontrollably, whereas at least this is only doing it when they hit. So you don't want a lightsaber that arcs. Definitely not. It's kind of a bit like Kylo Ren's one. Looked like it might arc. I would not want to be using his lightsaber. That's why I've left it behind me.
So I think we've probably got to draw to a close. So thanks for joining us, everybody. Thanks so much, Martin. That was amazing. Yeah. So if you guys have any extra questions, I'm sure you can email them over to me, and I'll pass them on to Martin, or do my best to answer them. But yeah, thanks so much for joining us today, and hopefully we'll see you all soon.